Hello everyone, I welcome you all once again to MSP lecture series on transfer chemistry. We have started discussion on classification of ligands by donor atom. So far I have completed discussion on hydrogen, carbon and nitrogen. I just began in my previous lecture and I gave little information about the donor properties of nitrogen and how the nitrogen behaves very similar to isocyanates and carbon monoxide. So that one can do some reactions. If you know a little bit more about how we can perform on bound nitrogen, some reactions that might be helpful in those who are working in the nitrogen reduction and carbon dioxide reduction and other such similar reactions. From that point of view, let me continue from where I had stopped. Let us look into the reactivity of coordinated nitrogen ligands or nitrogen donor ligands. So, how this electrophilic attack by H or any other electrophiles results in new products that we can see in a couple of reactions by choosing very specific examples. Let us consider a simple phosphine and nitrogen complex. So, when we have phosphines and when we try to put dinitrogen, we should remember we should go for very strong sigma donor ligands. Among phosphines, if we have alkyl groups, they are good sigma donors. From that point of view, you can see in most of these reactions we are using alkyl bound phosphines, not the aryl, and of course here to have some moderate sigma donor ability, one can also replace one of the alkyl groups with aryl groups such as phenyl. So, when this compound is treated with HX, so in this reaction one of the N2 is liberated, whereas the other N2 is reduced to form this kind of product. Diphos is a bidentate ligand. I shall show you the structure. Okay. Diphos is nothing but this is the one 1,2 bis-diphenyl phosphinobenzene. The mechanism of N2 reduction in biological system is not really clear. However, the reactivity of coordinated N2 is well studied. The reaction involve usually hydroxido, imido and nitride species. The possible reactions one can anticipate are electrophilic, nucleophilic or coupling reactions. So, now let us look into the electrophilic attack by H or other electrophiles. The same reaction I am considering again. The addition of Rx here can leads to CX bond cleavage and radical reaction. Now let us look into nucleophilic reaction. What would happen if a nucleophile attacks the nitrogen center? A manganese complex is chosen for this purpose, having cyclopentadienyl ligand and 2 carbon monoxide. When this is treated with methyl lithium, initially it forms an intermediate of this type. Of course, here counter cation is lithium. On further treatment with Me3O, BF4, a good methylating agent, and when we treat this with a typical alkyl magnesium such as diethyl magnesium, it gives an interesting magnesium complex having 2 cobalt moieties. Okay, so this ethyl group, it abstract hydrogen from cobalt hydrogen bond to give C2H6. And of course, here we have this reaction is carried out in THF. So, this is another reaction that depicts the nucleophilic reaction of coordinated nitrogen. So, with this let us move on to consider another interesting ligand called nitrosyl ligand. Nitric oxide, we call it as nitrosyl, okay, NO, is a bioregulatory agent produced endogenously. Disturbances in the production and regulation of NO are known to cause central nervous system disorder and asthma, besides many other diseases. Iron nitrosyl complexes help to balance the beneficial effects of NO against its potentially fatal effects. Of course, one should remember the fact that NO is also a very toxic gas. Now, let us look into the MO diagram of NO before we proceed for preparatory methods and reactivity and other things. You can see here the MO diagram, and of course, if you count valence electrons in case of NO, 6 electrons are coming from oxygen and 5 electrons are coming from nitrogen. So, that means we have totally 11 electrons. So, 2s electrons can be left for all practical purpose, because they are not adding anything to NO bond. So, now you consider 3 electrons, and of course, here 2 electrons are there, they form anti-bonding and bonding. What is interesting is about 2p electrons here and 2p electrons here, and if you see here we have 4 electrons and here 3 electrons. If you start filling in this fashion, we will be left 1 electron in anti-bonding orbital. That leads to the bond order of 2.5. So, that is the reason why NO has a tendency to lose one of the electrons readily is to have bond order 3. So, the moment you remove this electron to generate nitrosyl cation, we have the bond order 3 and that is stabilized. So, because of this reason NO acts as a nitrosyl cation. So, let us look into the binding properties, and of course nitrogen has a lone pair here, and that lone pair can be readily donated to the metal to form a sigma bond, and this is sigma donation. Okay. And then in the linear fashion, when it binds, the angle should be around 180 or it will be close to 180, and when it binds in bent fashion, what happens? It can have an MNO angle of about 120 degree here. And then because of the presence of pi star orbital, you can anticipate back donation with NO as well, very similar to carbon monoxide, and this is how one can show the interaction of filled metal orbital with pi star of nitrosyl ligand. This is back bonding, that means this also a sigma donor as well as a pi acceptor. And the relative strength also I already showed you couple of times earlier in a table, you can refer to it if you want once again. So, this one again I am bringing to show what would happen when a metal binds. So, that means this MO diagram depicts the interaction of NO with metal. So, now you can say the focus should be only on these electrons that can go as sigma to the metal. So, you can see here these two electrons are donated to appropriate metal orbital. So, either dx square minus y square or dz square to establish a sigma bond, and then metal has electrons in dxy, dxz or dyz. So, those things what happens, they can be shared with pi star of this one. So, pi star and metal d orbital having pi symmetry would overlap again to generate pi bonding and pi anti-bonding orbital. So, in which these electrons are placed. So, this represents back donation from metal to NO, and this represent NO to metal sigma bonding. Okay. This is a typical MO diagram for a metal nitrosyl complex. Now, let us look into the properties of linearly coordinated NO, and of course, one can also see the similarities between the way I have written the movement of electrons from oxygen to metal through nitrogen here, and this can be very similarly compared to what would happen with carbon monoxide with minimum back donation and maximum back donation, with of course having sigma bond intact. In the same way one can also write, you can see here when there is minimum just sigma donation, this would happen. When slightly back donation is there, this bond is weakened, this bond is strengthened. So, this the three extremes one can think of in case of NO ligand as well. So, when it is detached, it leaves as a nitrosyl cation, so leaving a negative charge on the metal. So, in that context NO plus is a 2 electron donor. If you just count the electrons, we have 10 electrons in NO plus, and similarly in case of carbon monoxide also 4 plus 6 10 electrons are there in the valence shell. So, it is obvious that both are isoelectronic, but NO plus needs to coordinate to a metal having 1 electron more. So, that means in order to generate nitrosyl cation, it has to bind to a metal and it has to give that electron, then only it becomes NO plus, and then that would be isoelectronic with carbon monoxide. So, that means 2 NO groups are equivalent to 3 CO groups. Let us look into the synthetic methods that are available for making NO complexes in the laboratory. Simplest method is treating directly NO gas. For example, let us consider CO2 CO8 and treat this one with 2 equivalents of NO. So, it is very interesting to analyze this one with the structure of this one, half a molecule of this one. You know why COCO4 cobalt tetracarbonyl exists as a dimer, because it is a 17 electron species, in order to satisfy 18 electron rule, what happens, it will establish a CO-CO bond and hence attains 18 electron. As a result, it stabilizes as a dimeric species, whereas in this case when you replace one of the carbon monoxide with NO, now NO is a 3 electron donor when it is linear. So, now it is 3 electron if it is giving, cobalt has 9 plus 3, so plus 6. So, 18 electrons are there. So, that is the reason this can be stabilized simply as a monomeric species. You should know the difference why it is stabilized as monomeric species, whereas COCO4 is not, means that is a 17 electron species and this is an 18 electron species. Let us look into another reaction where we are using a reagent of different type to generate metal to nitrosyl bond. Let us consider FeCO5 and treat this one with ppn. I am not sure whether you are familiar with this cation. It is a very bulky cation usually used to stabilize anions. I shall write the structure of that one later after completing this equation. So, you take this one and treat this with NO2 salt in isotronitrile. It is a counter cation and what we get is FeCO 3 NO minus plus CO2 plus CO. So, now let us count the electrons here. So, if we take Fe, that is 8 plus 6 plus 3. So, one negative charge is there. So, you will understand why negative charge is there on this one, because in order to satisfy, because we have taken out 2 carbon monoxide and 4 electrons have been taken out and in its place we have only one NO, that is a 3 electron donor. So, with this charge it becomes 18 electron species. So, everything one should explain very satisfactory, provided we understand this method of electron counting. Now, we must have realized how important it is to know how to do electron counting. And ppn, what is ppn? ppn is nothing but this bulky cation and NO2 here is neutral. So, this is called ppn. Let us look into a couple of more methods of preparation of nitrosyl compounds. Let us consider now very different one. So far we discussed with 2 metal complex in 0 valent state. Now let us go to another metal in high valent state, osmium tetroxide. In osmium tetroxide, osmium is in +8 state. So, when this is treated with NH2OH HCl in presence of NCS isocyanide ligand, thioisocyanide ligand, one can make so this is another way of making nitrosyls with metal in high valent state. Okay. Let me write another interesting reaction here. Let us consider rhodium chlorocarbonyl bistriphenyl phosphine complex. When this is treated with NOBF4, okay. So, now let us count electrons here. So, this one let us go with the neutral method. So, this is now cationic. So, this is in +3 state. If you go with this one 9 plus 1 plus 2 plus, I will leave it here, and plus 4. So, now if you see 16 plus now this is 3 and now the charge is now positive. So, we have a negative. So, since positive charge is there, you subtract 1. So, it goes. So, it is 18 electron species. So, you can always verify this way to know what kind of donor NO nitrosyl group is. Since I told you nitrosyl is both, it forms bent 1 electron donor and also when it is linear 3 electron donor. So, this helps in understanding this one. I think these 4 methods are sufficient, and if you are interested in looking into more methods, always you can go to right kind of textbooks. Now, let us look into the reactions of coordinated NO. So, due to the difference in the electronic structure of linear and bent coordination modes, I already mentioned reactivity of coordinated NO can be very different. So, linear MNO groups can be readily attacked by nucleophiles, whereas in bent structure lone pair on nitrogen are susceptible for electrophilic attack, but there can be some exceptions, and reactions of linear MNOs, that is linear metal nitrosyl bonds with nucleophiles such as OH minus, OR minus, SR minus or NH2R usually occur at the nitrogen atom. You should remember, when reaction happens with linear MNO with nucleophiles, the reaction usually occurs at N atom and also can occur at oxygen as well. So, well known example is a nitroprusside with hydroxide ion to give a nitro complex. Well known example is of nitroprusside with hydroxide ion to give a nitro complex. I think let me continue showing some of these reactions in my next lecture.